Hi, this is Chuck. Welcome to this first video in what will prove to be a series of videos on using power series to solve differential equations. First thing I want to do is take a look at what's a power series. It's something that you should have looked at and learned about in your calculus class. But if you'll recall, a power series is going to be a summation, and the summation can either go to some finite value or to infinity. In our case, our solutions are going to involve summations that go to infinity. And essentially what this is just the addition or the sum of a series, in this case, an infinite series of terms, where the index n increases by 1 each time. So n is just a counter. So for the first term, n is 0, then n is 1, then n is 2, and we continue writing terms by increasing the counter by 1 each time. Well, that's kind of an interesting idea that this could be used to solve a differential equation. Before going in depth in how to solve differential equations using power series, I want to do a first video here where we're going to take a look at how could this even work. Then I want to do in additional videos brief review of how do you work with power series, how do you shift indices, how do you add them, how do you subtract them, what's going on. And then after having laid this foundation of, gosh, this really can work, maybe I need to revisit my knowledge on power series, then we'll get into the actual solutions using power series. Let's take a look at a first example here. This is a first order linear homogeneous equation. It's equation 1 listed right there. You can probably look at this and figure out the solution to this yourself. It's going to be some constant times e to the x. For example, 4 times e to the x. If we just jot that down, y equals 4 times e to the x, you'll get that the derivative itself is also going to be 4 e to the x. Substituting those into the equation, you'll see, hey, that does work. They subtract off. You can use any constant in place of that 4 that you want, and that will also be a solution. So essentially, the solution to this is going to work out to be e to the x times some constant. Well, let's take a look at how we can use a power series to come to this solution. What we're going to do is we're going to initially start with y equals to our power series, where n goes from 0 to infinity. Recalling that at n equals 0, we have a sub 0, x to the 0. Remember, this can just be written as a sub 0 because x to the 0 is 1. The second term is a sub 1, x to the, and remember there really is an exponent of 1 there. It's just assumed to be there so we don't write it most of the time. Then you have a sub 2x squared plus a sub 3x cubed all the way up to infinity. Now, when we go to take the derivative of this, we're going to take the derivative of this term by term. Well, recall that this first term can be written as a sub 0. It's just a constant. As you know, the derivative of any constant is 0, so that's going to be the 0 plus then the rest of the sum or the series there. I've just left it out because 0 plus anything is still whatever that anything is. When we move to the next term, a sub 1 times x, we're just going to get a sub 1. Then as we move into additional terms, when we take the derivative of a sub 2x squared, remember that the exponent 2 from the x squared is going to come out front, and we're going to get 2a sub 2x with the exponent reduced by 1 in power. So it's just going to be 2a sub 2 times x. Similarly, when we get to a sub 3x cubed, we're going to wind up with 3a sub 3, and the exponent on the x is going to be the 3 minus 1, or x squared. So what's going to wind up happening here is we're going to get a series where we're going to have whatever the index is as a coefficient out front, and the exponent being 1 less than whatever that index is. So we can rewrite this series as the sum n starting at 1. We could start it at 0, and I'll talk about that in a minute, but we're going to have a sub n times n times x to the n minus 1. If you wanted to, this could also be written as n times a sub n, which is what you're actually seeing in the series that we're working with. Notice we have the 2, 3, 4 times a sub whatever it is. Okay, so this is actually the form that it's in. Now, I'd also mention that we could have started with n equals 0. If we start with n equals 0, notice that this first term is going to be 0 times, and it doesn't matter what the rest of it is, that first term is going to be 0. It's going to routinely be the case that we can start our series at any of a number of different indices, or let's say at most 2 indices, sometimes 3 or 4, depending on what derivative we're working with. But the point is we can start our index at a variety of values and wind up with the same series. Here we could have started this at n equals 0, but as we've just discussed, the first term would be 0, which is of no real concern. So we can write this as starting at n equals 1. When we take and substitute our y prime and our y, represented with these power series, into our original equation, y prime minus y equals 0, what we're going to get is this series that we just talked about right here that starts at 1 minus the original series, which was y, and our y value is up here. And we're going to have the series representing the derivative minus the series representing y. There are a couple things we need to do here before we can actually perform addition, subtraction, or whatever else we may want to do. The first thing we need to do is we need to ensure that the exponents on our x's are the same. The next thing we need to do is to make sure that the index at which we start, the starting value for our index, is the same. We can't start counting at 2 different values. Okay, so the first thing we're going to do here is to try to align the indices. Now, in the case of the y prime power series, I'm going to get that where my index starts at 0, so it will match up with the index on the second power series. So what I'm going to do is I'm going to say, look, I'm going to call x, a new name for the index, is n minus 1. Why do I want minus 1? Well, I want to start one smaller than where n is right now. If n started at 2, this would be k equals n minus 2. If n would have started at 5, this would be k equals n minus 5, and you get the idea. When I work this out, okay, I define what I want my k to equal. I can then solve for n by adding 1 to each side, and my n is equal to k plus 1. Okay, so on the left-hand side here, I know that my n is the same thing as k plus 1. Substitute that in. The second power series, I'm going to leave alone. Okay, I'm just focusing on redoing the first one. Notice in every position where there was an n, okay, so if we take a look here, we had an n, it's now replaced by k plus 1. We had an n, it's now replaced by k plus 1. We had an n minus 1, so we're going to have k plus 1 minus n. So what I've done is every place that there was an n, I've replaced it with k plus 1. Then what I'm going to do in this first power series is I'm going to simplify in each location where I can. For example, with our index, we have k plus 1 equals 1. Well, if I subtract 1 from each side, I get k starting at 0. My k plus 1 in the coefficient is going to stay k plus 1. My k plus 1 is the subscript count on my series coefficient is going to stay k plus 1. But look what also happens to my exponent. I have k plus 1 minus 1. The plus 1 minus 1 subtracts off, which leaves me with this leading power series with k equals 0 to infinity. I have k plus 1 times a k plus 1 times x to the k. It really doesn't matter what I call or what name I give to the index. I could call it k, I could draw a smiling cat face, I could draw whatever. It could be a, b, c, whatever you want. I would suggest not using a because that's already used here for our coefficients, and definitely don't use x, but you get the idea. So what I can do is I can take this first power series now. The good news is it starts at 0, just like the second one, and the coefficient on the x is just the index, which is the same thing there. So that's good news. We have several different concerns now taken care of. And what I'm going to do is, in the case of this first power series, instead of k, there's nothing particularly special about k, it's just a squiggle mark on the screen. I'm going to replace that with a different shaped squiggle mark, n. Okay. So what that gives me then is my first power series is going to be n equals 0 to infinity. Remember, the k plus 1 is going to become n plus 1. A sub k plus 1 is going to be a sub n plus 1. X to the k is now going to be x to the n. The cool thing here now is both of these power series start at the same point. They both end at infinity, and they both have an exponent on the x that's identical. This is great because at this point now, what we can do is we can take and we can start term by term adding these two power series together. Now remember, what's going to happen is on every term, what we're going to have is something that looks like n plus 1, a sub n plus 1. Then I'm going to have minus a sub n, and both of these are going to be times x to the n. If you prefer, I could have written this as each term is going to be in the form x to the n minus a sub n x to the n. I can factor out the x to the n's. When I do that, I'm going to have this n plus 1, a sub n plus 1. Now remember, I'm factoring out the x to the n, so I'm going to be left with an a sub n, and the x to the n will be outside of the brackets. This leaves me inside of the brackets with what should be numbers. Okay. This gives me this coefficient in front of the x sub n, allowing me to restate this as a single summation with the one thing minus the other. And the coefficient will hold true for all values of n from 0 all the way up to infinity. Okay, so what we need to do now is to get a handle on what are these coefficients going to look like as the index progresses from n equals 0 to n equals 1 to n equals 2 to n equals 3. Well, to get an idea of what that's going to look like, I'm going to take and first look at the term where n is 0. When n is 0, that means I'm going to plug a 0 in for n, and for n. And for the moment, I'm just going to focus on the coefficients. So what this is going to give me is 0 plus 1 times a sub 0 plus 1 minus a sub 0. When you distribute this, we're going to have the a sub 1 times 1, And what this is going to give us is a sub 0 is the same thing as a sub 1. That's going to be important to hold on to as we progress through the values of the index. Next, I'm going to set the n value, the index, to a value of 1. As we did in the previous example, I'm now going to introduce 1 for n in the top line on the screen. So that's going to give me 1 plus 1 is 2. So this is going to give me the 2. A sub 1 plus 1 is going to give me a sub 2. And then minus a sub 1 is going to give me my a sub 1. Okay, so we've seen where those terms come from. And it's going to equal 0. Why is it 0? Well, in order for this sum on the first line on the screen to equal 0, the coefficients need to equal 0. They need to add up to 0, okay, for n equals 0 up through infinity, which is why we will in each case say, you know what, that coefficient better be 0. Now, in this case, I can solve for a sub 1, and I get a sub 1 is equal to 2 times a sub 2. If I then solve for a sub 2 is going to be 1/2 a sub 1. The nice thing about knowing what a sub 2 is in terms of a sub 1 is I can replace the a sub 1 with a sub 0 from up here in this previous line of work. And this will then give me that a sub 2 is 1/2 a sub 0. That's important. And you're going to want to write this down somewhere. So a sub 2 is 1/2 a sub 0. Okay. Next, moving to n having a value of 2, I can substitute that into this first coefficient. And 2 plus 1 is 3. A sub 2 plus 1 is going to be a sub 3. A sub n, well, n is the 2, is going to give me a sub 2. So at this point now, I have 3 times a sub 3 minus a sub 2 equals 0. If I solve for a sub 3, okay, so in other words, I move the a sub 2 to the right-hand side and divide by 3. I'm going to get that a sub 3 is 1/3 a sub 2. But I know that a sub 2 is 1/2 times a sub 0. So I can rewrite a sub 3 is equal to a 1/3 times a sub 0. Well, that's going to be times 1/2 a sub 0. And as we continue this pattern, and moving on, we'll take a look at one more. If we let n progress to a value of 3, we're going to have 4 a sub 4 minus a sub 3. Once again, this is going to be set equal to 0. I can solve for a sub 4 by adding a sub 3 to both sides and divide by 4, which is where this equality came from. So a sub 4 is going to be 1/4 a sub 3. When we rewrite a sub 4, we're going to have a 1/4, and we can now bring along what a sub 3 is equal to. Well, that's 1/3 times 1/2 times a sub 0. So this then gives me that a sub 4 is going to be 1/4 times 3 times 2 times a sub 0. And I think you're seeing a pattern here. I hope you're seeing a pattern here. We could quickly write down that a sub 5 is going to be 1/5 times 4 times 3 times 2 times 1 a sub 0. And you'll notice that whatever value we choose for n, that nth term coefficient is really going to be 1 over, well, here we had 5 times 4 times 3 times 2 times 1. That's really 5 factorial. But in the long term, it's really going to work out to be 1 over n factorial, and it's going to be times a sub 0. Okay, so if we go back to our original setup, recall that we had y is equal to n equals 0 to infinity, a sub n, x to the n. But we know what a sub n is equal to. We can replace a sub n with 1 over n factorial a sub 0. So if I take this a sub n and I replace it with this, I'm going to have an a sub 0 there. Now, one of the things to be mindful of is a sub 0 is different from a sub n. A sub 0 is a fixed value. Notice the index doesn't change. It's always a sub 0, which means that we can factor that out front of the summation. And what we're going to have left inside of the summation is going to be the 1 over the n factorial. Remember, the n stays inside because it is still subject to the value of the index, x to the n. Okay, this can be rewritten then as a sub 0 times, and this may test your memory a little bit, but this summation here from 0 to infinity of x to the n over n factorial is the definition of e to the x. So what we have is a sub 0 times e to the x. Hey, wait a minute. Y is equal to some constant times e to the x, which you knew from the very start, but now we have a mathematical proof of that. And ta-da, there you go. You have the answer. Now, was this more efficiently solved by going through all of this? No, but it is a very nice first example to allow you to see why am I even concerned about using a power series. This can be used in locations where things like variation of parameters and all kinds of other good stuff like that that we've already studied isn't going to get the job done for us. I realize that the example we looked at is a first order differential equation. We're going to use this technique, the power series technique, in solving second order differential equations. Okay, well, before I move further into solving second order differential equations using power series, I want to do a quick review of working with series. I want to make sure that we get some review in on convergence and divergence. You need to know when a series is converging or diverging. You need to recall how do you compute the interval of convergence. We need to be able to change the indices. Remember, we talked about they don't always start at n equals 0. You're going to wind up with some situations where you may have n equals 5, and another summation n equals 3, and another one n equals 0. And you've got to get those all lined up so that they are all starting at preferably n sub 0. And we're going to look at some other useful ideas. We'll start working at this, which is going to be a quick review of power series in a second video. I'll see you there.